Hi everyone, welcome to Bright Mind Tutors. Today we are diving into super important concept in your HSC, which is equilibrium constant and Le Chatelier principle. This is going to be a pretty brief video. We're going to sum up everything in form of key points. So let's start. So what do you think? Here we have these two reactions, this and this. So what are you observing? Like, can you think of a difference between these two reactions? Like, take a minute and think, how they, other than they have got different products and the reactants, what else, on what conditions they differ? So if you check nicely these pointers, the pointer of these arrows vary differently. They differ. This one is like a single-headed arrow and this one is like a two-way arrow, like a half-headed two-way arrow. So these kind of arrows represent reversible reactions. Reversible reaction means my reactant is converting into the product, but my product is also getting converted into the reactant. So it's a kind of two-way process, and also it's a half head, and this is like a fuller head. Half means some amount of my reactant is going into the product, and then there is a half head other way around, which means some of the product is disintegrating back into my reactant. So these kind of reactions are known as reversible reactions, and we need to know them by heart for the chemical equilibrium. So this is the definition. Basically, reversible reactions are those which proceed in both forward and backward direction. Now again, there is this keyword, what is forward and what is backward. Forward basically means that's going to lead to the product formation, and backward means that's going to lead to the reactant formation. You know how this is going to be my forward reaction in which sodium carbonate and calcium chloride are getting formed, and in my backward reaction calcium carbonate and sodium chloride are getting formed. Okay, I hope it works. Okay, let's move further. So now comes what's the chemical equilibrium. So it's a simple definition which says, first of all, the keyword is it occurs always in a reversible reaction when the rate of formation of the forward reaction is equal to the rate of formation of the reverse or the backward reaction. Now, what does this mean? It's a quite fancy definition. So, and you have to learn it as it is because we're going to get few keywords. This is fitted with some really nice keywords that going to, enhance your marks basically. So it says, I guess the reversible is quite clear. It says that the rate of forward. Rate is a kind of speed. So how we express, rate basically means, change in concentration, either of your reactant or, if I'm talking about the rate of forward reaction, how the change in the concentration of your reactant divided by time, that is the rate. So chemical equilibrium means like occurs when whatever the at whatever rate your reactants are getting consumed is equal to the rate at your products are getting disintegrated. At whatever speed the reactants are moving in this direction, the product's gonna move back in this direction. So the same rate, not the concentration and the rate are two different things. Just mark it, just fit it in your head. Concentration and rate, they are different. Rate is this, it's how the concentration is changing per unit time. And then this is pretty important. At equilibrium, basically the concentration of the reactants and products are constant, they are not equal. So what does this means? Let's try to decode it. Like suppose I have a reaction, like a reactant forming product, and I say, now at equilibrium what's going to happen is, like if the reactant is this mole per liter and the product is maybe 6 mole per liter, they could be this at equilibrium. Okay, they could be this at equilibrium. The concentrations aren't equal, equal. The rates are equal. When I divide these concentrations by certain times, like I have 5 mole per liter divided by T1, it's gonna equal to 6 mole per liter divided by time T2. Time, this thing is equal but not the concentrations. I hope it's clear. It's pretty confusing, so that's why I'm stressing on this. Okay, now let's try doing this question. Just read it, like pause the screen for a minute, do this, try doing this question. Okay, so let's try doing it now. it says, equilibrium exists between some calcium carbonate, which is my reactant, and calcium oxide, carbon dioxide as product. I just need to write the expression for it. So let's try writing the expression. I'm going to write it in a formula equation form. You can, you should also try writing it in a formula equation form. So the calcium chloride is CaCO3 that exists in equilibrium with my product, which is calcium oxide plus carbon dioxide. This is the answer. Okay, I hope it's clear. Let's move further. Do learn this definition, please. Learn it. Okay, now the thing is, what is Kc? So let's try to define the Kc first. Kc is a kind of equilibrium constant, okay, and it's expressed in mole per liter. That's the SI unit of the concentration. And now what Kc tells, it's a kind of concentration, like it's a kind of ratio of the concentration of my product to reactants, basically at equilibrium, obviously. So let's take like a hypothetical reaction, and we will try to write the Kc for it. And the C actually means concentration. So suppose I'm taking this reaction A, B, it's an equilibrium with C plus D. Now what are these A's, like small, what are these small letters? These are basically smaller ones are, these are coefficients that gonna appear in the balanced equation. These are the coefficients of balanced equation. And then what are these A, B, C, D's, capital ones? Capitals are, these are basically concentrations that appear at equilibrium. Like what are the concentrations at equilibrium? Okay. So let's try to write the expression. So the Kc will be capital K and a lower, like pretty lowercase c. It's going to be product. So write it C, put it in the square bracket, raised to power C, again a square bracket D, raised to power small d, divided by reactant A, put it in the square bracket, small a, and then a B raised to power B. So this is the expression for equilibrium. So whatever I have written, it actually means the same way only. See, these are my square brackets. Squared in the chemistry means that is known as active concentration. It's a short trick for concentration. Whenever there is a number inside the square bracket, it technically means we are referring to the concentration, that also in mole per liter. So it is important. And now we have to raise them to the power of their coefficients, which gonna appear in the balanced chemical equation. I hope it's clear. Now again, this is very important key point, which says, whenever we are writing these, the state symbols are pretty important. This needs to be aqueous, gas, or whatever. These are important. The state symbols are important. They say whatever comes in the expression of Kc should have a state symbol of gas or aqueous only. Solids or pure liquids, we don't write them. We don't consider them. They are never written. They are ignored. They are actually equal to 1. So ignore them. And then the second, and it's pretty important, it says, they say on what factors the Kc depends. So you need to keep in mind that Kc depends only upon temperature, no other factor, just temperature. Like you can switch the pressure, you can switch the concentration, you can switch the volume, but the Kc is dependent only on temperature. I hope it works. Now we have this again question time. I'm going to solve the first question for you, and you're going to try doing second and third, and you can ping the answer in the chat box. So in the first one, they're asking us to write the expression for Kc. So I know Kc is again like concentration, and we just read it. We just need to consider aqueous and gases. That's it, nothing else. So if I look at my product, I can literally spot only one aqueous. So I'm going to write copper plus 2, I'm going to put it in the square bracket, divided by, in my reactant side, still one thing is in, just there is only one thing which is in aqueous. And then I'm going to write Ag plus square brackets. And you can mention the state symbol if you like. If you don't like, you can just ignore it. And next part is, I can still see a 2 in front of Ag plus, so I need to raise it to the power. That's my expression. Kindly do the second and third one, please. Okay. And now the next point is, we have this again like a key point which says the value of the Kc. It is actually a number. We can actually find it. So it says if the Kc is it's bigger than 1, there are two cases. Kc is going to be bigger than 1 or Kc is going to be less than 1. So if Kc is bigger than 1, let's take two cases actually. One, the Kc is 0.05, just imaginary number, and the other, like, let's maybe take 2. Now if you check, in the first case, the Kc is less than 1. If Kc is less than 1, it means you're going to have more reactant. So, your reaction mixture contains more reactants. There is like more concentration of the reactants. And if Kc is bigger than 1, basically your reaction has more concentration of product. Okay, again, very important. Just make a key point of it. Let's move further. And now the next part we have is Le-Chatelier principle. Just a simple definition, you need to, learn it. Learn this definition. So it says, let's talk about it. So what, let me give you like a raw background behind it. So the raw background says, whenever equilibrium is set up, so that equilibrium is governed by certain conditions. Like there's going to be like a temperature condition, pressure condition, concentration condition, and the volume condition. So if you try to alter any of those conditions, your equilibrium fluctuates, your equilibrium disturbs. He says, I hate change. Equilibrium particularly hate change. It don't want any of its variable to get disturbed. But when you try changing those variables intentionally, equilibrium tries to move in some direction to counter the change, which is clearly written in this definition. Just read it, write it, learn it. So the variables are pressure, temperature, concentration, whatsoever. Equilibrium shifts to offset the change. That's it. Okay. So now here we have got the factors that affect the equilibrium. I have summarized them in a really brief way. It's a kind of trick only. Just take a screenshot of the slide and learn it. So like if I talk about the concentration, the very first factor, if you try to add the reactants, so according to the Le-Chatelier principle, equilibrium is going to get angry while you are adding the reactants. I don't want the reactants to be added to me. So what equilibrium will do? Equilibrium will try to shift into some direction, to counter the change. So it will try to do something so that whatever the extra amount of reactants have been added, I want to consume them. If it wants to consume them, basically means it's going to make more product. So if it's going to make more product, we will say forward direction. The equilibrium tries to move in the forward direction. Similarly, there are pressure. Remember one thing, the pressure thingy is only used in the case of gases. No other state symbol is affected by pressure. Like solid, liquids, aqueous, no effect of the pressure. And then we have the temperature. Like there are two types of reactions again, exo and endo. Just simple thing, if a reaction is exothermic, means exo means it's already liberating the heat, and you try to increase the temperature. Now the equilibrium is like, oh, I'm already giving out heat and you're providing me more heat. No, I want to absorb whatever extra amount of heat you are giving me. I want to absorb it. So if I want to absorb it, it's going to move to the reactant side, which is my backward direction. So one important part here is, if I take a reaction like this and I say, delta H is negative, like the forward is, if I say forward reaction is exothermic, so it's quite obvious that the backward is automatically endothermic. Okay, just remember this. That's for the, and for the endothermic one, delta H is bigger than, it's a positive number, basically it's bigger than 0. Okay, and the last part is catalyst. Catalyst has no effect. Catalyst just plays with like activation energy, nothing else. No shift, it won't, but it just helps the reaction to be faster. Okay, so now I'm going to do this question for you. Suppose I'm increasing the pressure. Pressure one is little hard, I personally feel, for students, but if you get it in one run, then it's fine. So let's talk about, I'm increasing the pressure. So let's try to calculate the moles first. If you, if you read, let's try to calculate the moles. So I have this gas, and heat. Okay. So total, let's say total moles of gaseous, gaseous components maybe on reactant side. How many are that? Just talk about, just look at their stoichiometries. These are what? This, and if there is nothing, there is always one in chemistry. So it's basically 4. And then if I talk about, total moles of the components on the product side. So how many are that? I can just literally spot one number, which is this 2. That's it. So there are 2 moles. Correct? There are simply just 2 moles. Okay. So now if I'm increasing the pressure, I know what happens to the equilibrium. If you try to increase the pressure, it tries to shift in the direction with the lower number of moles. Okay. So which direction has lower moles, lesser moles? Product side. So if you increase the temperature, equilibrium, pressure, if you increase the pressure, equilibrium shifts to right. Shifts to right with fewer moles. That is, right is, for right you can write forward also. That's it. Okay. The next part is if I try to increase the temperature. Now the delta H value for this reaction is given to me. It's releasing heat, Reaction is basically, the forward reaction is exothermic. Exothermic means it's already liberating out the heat, and I'm trying to increase the heat now. So now what's going to happen? Think. So it's going to shift to the direction such that, it says, I want to absorb that extra heat added. The system will try to shift in some direction to absorb whatever extra heat I'm adding. So it's going to shift to the backward direction because the backward is endothermic. And what is the definition of endothermic reaction? The one that absorbs the heat. Okay. So for this one, the equilibrium shifts to the left side or backward, whatever you want to say. Okay, I hope it works. Now we have few HSC style questions that you should, try attempting. We can do them together. I'm going to mark the answer, pause the screen for a minute and try doing these. The first and the second one are pretty simple. They're straight answers. Okay, I hope you are done. So see, they are saying, what would lead to the higher concentration of ammonia? Like I want to produce more and more NH3. If I try to increase the temperature, no, the reaction is already liberating the heat, so I can't, And let's try to rule out the options. Like D says adding a catalyst. Catalyst actually has no effect. Decreasing the nitrogen. Okay, if I try to decrease the nitrogen, what's going to happen? The equilibrium says, oh, I'm getting rid of nitrogen. Now I need to make more and more nitrogen. So it's going to, disintegrate more and more NH3 back into N2. The only option left is B, increasing the pressure. Okay, this one without any explanation, we know the catalyst does not have any effect on Kc, no change. Okay, now the third question, it is pause and try if you can do it, otherwise I'm going to solve this one. So they're asking the exact numerical value of the Kc. So we know that Kc is equal to, let's try to write the expression of Kc for this. Hi in the square bracket raised to power 2, because they all are gases, it's completely fine. Then H2 square brackets and I2 square brackets, and then you just need to substitute these values. What is Hi given to you? 0.6 square divided by H2 is 0.2 and I2 is 0.2 again. So just solve it and you're going to get the option C. That's it. Okay, this is going to be your answer for this. Okay, now here is this question. This is like a practice problem for you. It's a 2-marker, again important for your exam. Try it and ping the answer in the chat box, or just drop the answer in your chat box, please. Okay, so here is like the entire sum of important key points that you need to keep in mind. Whenever you're trying to do the questions, always try to do them in a balanced, always make sure the equations are balanced. Then always apply the Lee-Chatelier principle logically. Like it's a logic only, whatever is given in the question, just think just prepare like a mind map in your brain. Okay, I need to counter this change. How am I going to do that? Just apply that. And then what Kc tells? Kc just tells where the equilibrium lies. That means you have more product or you have more reactant in your mixture. Basically, if you have more reactant, it means your reaction is actually technically failed, because you aren't getting the desired amount of the product. And then again, practice a lot of questions. And the last thing is, if you like this video, you can subscribe the channel, and you can also check the exclusive HSC plans to achieve your desired grade. And you can find the important links in the description box. You can enroll for a free demo session. You can customize. There is a lot more. Just check out our website. Thank you. Happy learning. Take care.